Okay, welcome back, ladies and gentlemen, to the 10th and final lecture in the series on Structural Analysis 1. Today we're discussing the stiffness method as it pertains to frame elements, and we're going to do a couple examples. So to begin with, we're interested in the analysis of frame elements. Now, what is a frame element? A frame element, in the context of the stiffness method, is any element that can be described by 3 degrees of freedom at each node. So this could be, for instance, a beam element that has axial degrees of freedom. It has lateral slash shear degrees of freedom, and of course flexural and moment degrees of freedom. For the sake of this lecture, we're going to ignore axial components. We're going to assume they are small, and so what ends up happening is we're going to be ending up with flexural and shear components of the degrees of freedom. So you can imagine we have shear components Fy1 for any element, and we also have My1, or perhaps we're just going to call this M1. We're also going to have an Fy2 here, and then M2. We call this Fy because we tend to construct a coordinate system that has the following sign convention. We have positive y going up and positive x going right. So because that force is going up in the upwards direction, we're going to refer to it by Fy plus the index number. Okay, so anytime we have an element that looks like this is our element. We end up getting a stiffness matrix that is 4 by 4 because we have 4 local degrees of freedom. And this stiffness element can be described as follows. So the forces are going to equal to matrix of constants multiplied by EI over all. And this is what the matrix will look like. We have 12 divided by L squared, 6 divided by L, minus 12 divided by L squared, and 6 divided by L. This matrix is going to be symmetric, so I'll put a symmetric symbol down here. We're going to be getting a value of 4 here on the diagonal, minus 6 over L to 12 L squared minus 6 over L, and lastly we get a 4 on the final component of the diagonal element. And so we close the matrix, and that's what we have. And the deformations that we're going to look at are y1, so y is the vertical component of node 1 here. So we have y1, theta 1, that's the rotational component of that node. We have y2 and theta 2. And we're going to close this vector. Here it is. And that's node number 2. So this is node 1 and node 2. And that's a frame element. Okay? So let's take advantage of this new stiffness method and do an example and see how it can be applied in some sort of frame analysis example. All right, so in this example, we're going to be looking at a 2-span beam element that is fixed at one end and has a roller connection. And there's also a force that is being applied at a 45-degree angle. So let's draw these. This is going to be my fixed connection on the left-hand side, and I'm going to denote this by A. I'll have a roller element here With rollers, I typically draw them as a ball. You could also draw them in all sorts of ways. Um, we have node B, so that's going to be 1 degree of freedom here. And I'll have this free end here that has no support reactions, so it's almost like a cantilever. It's up in the air. And over here I have 2 local degrees of freedom. So I have the vertical component, and I have this rotation here. Let's call this 2 and 3. And the forces that I have are as follows. I have a diagonal force going down here. Its magnitude is equal to 5 kilonewtons. And this rotation, or this angle here, is in fact 45 degrees. And so we're interested in analyzing this indeterminate beam structure and identifying what the rotations and deformations are at the locations of the degrees of freedom. And these degrees of freedom that we've noted down are the global degrees of freedom. Okay? So the last component that we're interested in is the structural properties. So the elastic modulus is given as 2 times 10 to the power 3 megapascals. So I'm assuming this is a steel component. IAB is equal to 200 times 10 to the power 6. The units are millimeters to the power 4. And IABC is the same thing, or perhaps actually it's a smaller value. We have 50 times 10 to the power 6 millimeters to the power 4. Okay? And the lengths of these elements are 8 meters and 5 meters. Okay, so we're giving the properties. We know what the local stiffness matrix looks like for each element. All we have to do is to really plug in the values of the parameters, like the lengths, the elastic modulus, and the values of I. And for the case of KAB, we get the following: 5E3, 3/16, 3 divided by 4, minus 3/16, and 3 divided by 4. There's the second row, and third and final row. There it is. Okay, so we close this matrix, and we ensure that it is symmetric. It has to be symmetric. The next thing we're going to do is to draw the local stiffness matrix for elements BC, or between nodes BC. So that's element, the second element. So this time we have 2e3, 2 times 10 to the power 3, and we get the constants 0.48, 1.2, 1.2, 4, minus 1.2, 2, 0.48, minus 1.2, and lastly we get a value of 4 down here. Okay, oops. Alright, so let's close this matrix, and symmetry. What we're going to do next is to formulate the global stiffness matrix from the local ones, and to invert the global stiffness matrix and use the available externally applied forces to find our deformations. So let's do that. Before we formulate our global stiffness matrix, we have to identify what the relevant degrees of freedom are for each element. So if I were interested in element number 1, I would draw element number 1, and then I would overlay the global degrees of freedom over element number 1. And so what I can see is that when I draw my local stiffness matrix or local degrees of freedom, my fourth local degree of freedom is overlapping with the first global degree of freedom. So what I'm going to do is to put zeros where I have no overlaps and put the index for the global degree of freedom where I do have overlaps. So what I'll get is that the relevant degree of freedom, or the relevant component of this matrix, is this value down here for the first element. As for the second element, we have to do the same thing, again identifying what the relevant degrees of freedom are and which of the global ones overlap with the local ones. So I have my beam, I draw my global DOFs, and again I want to identify which of my local ones are overlapping with the global ones. Oops. So we have 0 at the location of the first index, because as we realized, there is no vertical component at that node. And we get 1, 3, and 2. Because that's a 1. So that's a 1. The vertical component on the right side is a 3. And the rotation one is a 2. So the components that are of interest to us are down here inside this rectangle here. Okay, so I have this value 4 and this matrix down here, and I'm going to assemble them into a global matrix. And this global matrix, because we have 3 global degrees of freedom, is going to be 3 by 3. So I have K global is equal to 28 E3 minus 2.4 E3, 4 E3, 960, 2.4 E3, and 8 E3. That's what we have. So now that I'm interested in finding out what the deformations are, I can draw my vector of, or I can list my vector of deformations. U1 through U3 is equal to K global, K global inverse times my externally applied forces. So PC cosine 45. And that's referring to the vertical component of the diagonal force with an angle of 45 degrees. And so we end up getting the following deformations. Seven radians. What's clear is that the rotational deformations tend to be quite small, and in real structures, deformations are in fact quite small. So this is nothing to worry about. And we have 1.945 millimeters. Okay, that's what we have in terms of the deformations. So let's just briefly or very quickly draw our undeformed structure and then deform it to see if everything looks good. So we had this kind of boundary condition and this roller here. And based on the results, we identified that we have forces going down, or excuse me, this node here going down. We also realized that there is a negative degree of freedom, rotational degree of freedom. So negative is clockwise in this case, because we identified positive rotation with the counterclockwise motion. Okay, and at the location of the fixed end, we have no rotation. So if I were to draw my deformed shape, it would look somewhat like this dashed line here. Let's see if I can draw. So somewhat like this, with this downwards deformation moving in such a way. Okay, and that's what really the deformation or the deformed shape looks like. I'll probably put a delta here to indicate that this is a deformed shape. And now we can move on to the next example. With the second example, we have another two-span beam. And this time we are going to be dealing with a uniform load. So here's my beam. I have a fixed end at the right-hand support. I've got a roller here. And I've got a roller at the left-hand support. And what's happening is that I have a uniform distributed load in the left span. And I also have a point load in the right span. And their magnitudes are given as follows. Okay, and I have nodes A, B, and C. And I've got lengths 8 meters, 3 meters, and 2 meters. Okay, so let's identify the global degrees of freedom. At location A, I have a rotational one. Obviously, we're disregarding the axial components, and we have a fix in the vertical component of this reaction. So there's only the rotational one. I have a second rotational one at B, and at C I've got nothing because all the degrees of freedom are fixed at that location. So what do we do with a case like this? So anytime we have forces between the nodes of a frame structure that, like this one, what we have to do is to introduce this idea of fixed end forces and fixed end moments. And that's what we're going to do in a second. For fixed end forces, what we have to do is to draw out these beam segments, and at the locations of the nodes, we're going to need to fix our beam or our frame elements. And what that means is that now that I have this distributed load, I need to know what my forces are at the locations of the fixes. So I need to know what these moments are, in this direction, and I need to know what this vertical support reaction is. So to do something like this, you need to obtain one of these beam formula documents that identify and demonstrate all sorts of very useful information with different types of beams and different types of beam loadings. And this document that I have is a very useful one. It's titled Beam Design Formulas with Shear and Moment Diagrams. It's by the National Design Specifications for Wood Construction. So I highly recommend that you obtain this document. I think what I did was to just Google this, and it's readily available, it's free. So you can easily download it, and it contains lots of useful equations and formulas. Some of these formulas are even useful to know and memorize because they tend to appear in professional engineering FE type exams, so you might as well know some generic examples like the ones provided here. So we're going to need one of these documents. Make sure that you have one available, and we're going to use that next. So I have a two-span beam, and I just said that at the locations of the nodes A, B, and C, I need to fix my beams. So this two-span beam is going to be divided into two different components. These components are going to be fixed. So there's a fix here, there's a fix here. So we have A, B, B, C. It's going to be another fix here and another fix here. And in the right-hand component, I have my point load, which has a magnitude of 20 kilonewtons. And when I look up my fixed end moments and forces, I tend to have, and hopefully I've done my math correctly here, I tend to get values that are 12.96 kilonewtons and 7.04 kilonewtons. So hopefully I've done this correctly. 9.6 kilonewton meter on the right hand side, that's for the moment, and I also have a 14.4 kilonewton meter for this component here. Okay, and let's not forget that we have the distributed load on the left component of this two-span beam. So I still have this distributed and uniform load here. It had magnitude of 20 or 2 kilonewton per meter, and when I look up the fixed end moments, I get a 10.67 kilonewton meter on both sides, and I also get vertical support reactions of 8 kilonewtons on the left and 8 kilonewtons on the right. Okay, so we've already identified the global degrees of freedom. We had this rotational one and the second rotational one. So we get a global stiffness matrix that is 2 by 2, 2E4, 1E4, symmetry, and 2.8E4. And this time, unlike the previous examples, we have these fixed end forces that we need to incorporate. If you recall, in the previous examples, we always had a force, and this force equaled the global stiffness matrix times our deformations. This time, we need to incorporate fixed end forces, and I'm going to denote that by PF. We don't have any nodal forces, so P is equal to 0. We only have the fixed end forces from the forces that are present between the nodes. And so what I have is Ku is equal to PF. And this time PF is going to be minus because we're moving it to the left-hand side of the equation. And so if I'm looking at my global degrees of freedom, the PFs are rotational. So I'm going to get two components, and they're going to be rotational components. So with the first one, I have a minus 10.67. And with the second one, I have a 14.4. Or excuse me, I have a plus 10.67 minus 14.4. So I have a minus 3.76. And you often have to spend a good amount of time to really comprehend and understand how the sign conventions work out here. So I highly recommend paying good attention to the sign conventions. This time we had a minus PF here. So of course all these values are already multiplied by the minus sign. But yeah, pay attention to that. So we have K global U is equal to minus PF. We invert this KG and move it over to the right hand side and end up getting a force. Our force is multiplied by the flexibility matrix, and we get a deform shape that has the following values: 5, 6, 7, E minus 3, and 0, 6, 8, 5, E minus 3. And again, E means times 10 to the power. We have radians and radians. All right? And lastly, what I want to find out is what are my excuse me, what are my elemental forces? So I have PAB is equal to KAB, and I know what my deformations are. I had a 0 here. I had a minus 0.567. E minus 3, 0 here, and 0.0685 E minus 3. Oops, let's do a better job at drawing this line. Here we go. And I cannot forget about my fixed end forces, so let's incorporate those. I had this 8 going up. This is the rotational one. With the stiffness method, we said counterclockwise is positive, so 10.67 is going to be positive. We have a value of 8 and a value of 10.67, and it's a minus. Okay, and if we have done our math correctly, we should get values that look like this. Okay, these are the elemental forces for the first element, and now we're interested in the right beam, the second span, so that's PBC. We have KBC, the deformations, 0.0685 E minus 3, 0, 0. I like to draw perfect lines, but it's very hard with these digital tablets. Plus 12.96, 14.4, 7.04, and minus 9.6. And again, these are our fixed end forces. And we're going to get a value of 13.12, 14.95, 6.88, and minus 9.33. That's it. If I were to draw my shear force diagram, it would look as follows. So let me draw 2 lines, copy paste, because I'm going to do my shear force and then bending moment diagrams. Here we have VFD, and here we have BMD. With the VFD, I have a vertical force going up and the diagonal line, which is due to the application of the uniform load. So I have this force going up, a value of 6.13, and I have a 9.87 down here. And 9.87 is a minus because we're down here. And then because I have this second roller support, I'll be pushed back up again. This second value is 13.12. So we have 13.12. And this time I need to go flat like that. And then because of the point load that is being applied, I need to go back down, go flat, and then let's draw this a little better, okay, and then go back up. So here it is. So down here we have a value of 6.88, and this is my shear force diagram. Okay. Secondly, I need to, oh, by the way, before we do that, let's put down the units because units are important, kilonewtons. Okay, the second component is looking at the bending moment diagram. And this time, with the bending moment diagram, I have, I need to calculate the area of this triangle, and I should get a value of 9.4 down here, units being kilonewtons meter. And now we're in the opposite direction. I need to find the area of this triangle. So when I do that, I go back up to a value of 14.95, and then I have the point load that is being applied. Here it is. And this value is 11.3 here, and oops, excuse me. This line needs to go back up because this is a fixed end support. Okay, so we have a value of 9.33 here. And this is our BMD diagram. And just to recap, what I did was to find the area of the first triangle, this triangle here, and that led me to a value of 9.4 here. Then I subtracted the value of 9.4 by the area of this triangle here, and that sent me to 14.95. And then I had to add the value of this triangle, so that took me back down to 11.3. And by the way, this is a rectangle, not a triangle. And lastly, subtracted the value of this rectangle, and that took me to a value of 9.33. So hopefully I've done the math correctly here. If there are any mistakes, please let me know. I'll make the corrections accordingly. And I hope this has been a useful lecture for you. This is the last lecture in the series. Hopefully what I'd like to do next is to start up a course on structural dynamics and then see where we can go from there. Okay, I'll see you next time.